Stephen Hawking once warned humanity not to signal aliens because they might come and conquer us. Stephen was brilliant. Stephen was also, on this specific question, not doing the physics. The physics says something far stranger than conquest. The physics says they can't come. Not won't, can't. And I want to be careful here because Hawking was my friend and he was right about almost everything. And when he was wrong in interesting ways that taught you something. This is one of those cases because the error isn't random. The error reveals something. It reveals that even the greatest physicists, when they think about aliens, stop doing physics and start doing science fiction. They start thinking in terms of ships and telescopes and radio signals and civilizations building Dyson spheres, and they actually forget to ask the first question. The question the universe answers before you've even opened your mouth to ask anything else. The question is this: what does the geometry of space-time actually permit? Not what do we wish it permitted, not what does Hollywood need it to permit to make the third act work. What does it actually physically, mathematically allow? And when you ask that question honestly, when you sit down with general relativity and thermodynamics and quantum mechanics and you do the numbers without flinching, you get an answer that is not ambiguous and not comforting and not a matter of opinion. The answer is not much. The universe permits almost nothing that the alien arrival fantasy requires, and the reasons why are not engineering problems. They are not funding problems. They are not problems that a sufficiently advanced civilization could solve if only they were clever enough. They are structural. They are baked into the fabric of space-time at a level so fundamental that cleverness is simply the wrong category of response. You can be as clever as you want. The universe doesn't care about clever. So here's what I want to do tonight. I want to walk you through the actual physics. Not the popularized version, not the maybe someday version, not the version that ends with a hopeful shrug. The real version, the one that has kept me arguing with colleagues for decades. And I promise you, I genuinely promise you that the real version is more interesting than the fantasy. Not more comforting, more interesting. There's a difference, and physics lives in that difference. Start with the simplest thing. Start with distance. The nearest star to our sun is Proxima Centauri, 4.2 light years away. That number is so familiar by now that it has lost all meaning. People hear 4.2 light years and they nod, and somewhere in their head they think far but manageable. The kind of far that a sufficiently motivated species could handle. The kind of far that Jules Verne would have called a good challenge. It is not that kind of far. A light year is the distance. Light travels in 1 year. Light travels at 300 million meters per second. In 1 second, light crosses the distance from New York to Los Angeles about 100 times. In 1 year, light travels roughly 9.5 trillion kilometers. Proxima Centauri is 4.2 of those. So the distance to the nearest star is about 40 trillion kilometers. The fastest human-made object ever launched, the Parker Solar Probe, at its closest approach to the sun, reaches speeds of about 700,000 kilometers per hour. That is extraordinary. That is a genuine triumph of engineering. At that speed, to reach Proxima Centauri would take approximately 6,500 years. 6,500 years at the fastest speed any human object has ever achieved to the nearest star, which almost certainly has nothing interesting on it. Now, the alien arrival fantasy doesn't require travel to Proxima Centauri. It requires travel between whatever distant civilization produced the aliens and Earth. The distances involved in any realistic scenario, a civilization that evolved independently in a different part of the galaxy, separated from us by tens of thousands to hundreds of thousands of light years, make Proxima Centauri look like walking to the corner store. But wait, people will tell you, speed is an engineering problem. With enough energy, with enough time, with enough determination, you can go faster. And this is where the physics enters the room and closes the door behind it. Special relativity sets the speed of light as an absolute limit, not a practical limit, not a limit imposed by our current technology, an absolute limit woven into the structure of space-time itself. As any object with mass approaches the speed of light, the energy required to accelerate it further approaches infinity. Not a very large number, infinity. You cannot reach the speed of light with a massive object. You cannot exceed it. This is not a hypothesis. This is one of the most precisely tested results in all of physics. Every particle accelerator on Earth has confirmed it over and over for 100 years. So the alien, whatever it is, whatever its biology, whatever its technology, if it is made of matter, it cannot travel at the speed of light. It can travel below the speed of light, and below the speed of light, the distances involved in galactic travel are not 6,500 years. They are tens of thousands of years, hundreds of thousands of years, millions of years, if the civilization is in another galaxy. Now here is where it gets strange. Special relativity does something that most people know about, but very few people actually absorb. Time dilation. The faster you move, the slower time passes for you relative to the stationary observer. At sufficiently high fractions of the speed of light, this effect becomes dramatic. A traveler moving at 99% of the speed of light would experience time passing at roughly 1/7 the rate it does for a stationary observer. At 99.99% of the speed of light, the factor becomes about 70. A journey of 70 years from Earth's perspective would feel like 1 year to the traveler. People hear this and they think, problem solved. The alien just travels fast enough, and from their perspective, the journey is short. They don't have to live for 100,000 years. They just need to go fast enough. This argument sounds right. It is also, when you look at the full physics, an argument that collapses under its own weight. First problem, energy. To accelerate a spacecraft, even a very small one, let's say 1 metric ton, a tiny fraction of what any realistic crewed vessel would weigh to 99.99% of the speed of light, you need an energy output comparable to humanity's total energy consumption over centuries. We're talking about numbers so large that they stop being numbers in any practical sense and start being a way of saying no. The universe is saying no. The energy required for relativistic travel is not a technological obstacle that ingenuity can overcome. It is a tax that nature imposes on anyone foolish enough to try, and the tax rate is essentially confiscatory. But let's set energy aside. Let's say, for the sake of argument, that the alien civilization has solved energy. They have a power source we can't imagine. Fine, I'll give them that. Physicists are allowed to make generous assumptions sometimes. It's called being fair to the hypothesis. Second problem, the interstellar medium. Space is not empty. It never was. Between the stars, there is gas, dust, cosmic rays, microwave background radiation, stray hydrogen atoms distributed at about 1 atom per cubic centimeter on average. At everyday speeds, this is nothing. At relativistic speeds, if velocity is approaching the speed of light, this is catastrophic. A hydrogen atom hitting your spacecraft at 99% of the speed of light hits like a very energetic cosmic ray. At the densities present in the interstellar medium, a spacecraft moving that fast would be bombarded by radiation intense enough to destroy any material we know of, and almost certainly any material we can conceive of, within a very short time. The universe, it turns out, has not made interstellar space into a convenient highway. It has filled it with a fine, dilute sandstorm that, at relativistic speeds, becomes a blowtorch. Third problem, deceleration. Everything I just said about acceleration applies equally to deceleration. You have to slow down at the other end. The energy budget doubles. Fourth problem, the traveler's subjective time may be compressed, but Earth time is not. If an alien civilization sends a ship that by relativistic time dilation takes 100 years of shipboard time to reach us, but that journey corresponds to 10,000 years of Earth time. Earth has changed beyond recognition. The mission profile makes no sense. You leave home, arrive at your destination tens of thousands of years later in the destination's reference frame, and whatever you are coming to find has had time to rise and fall and rise again a dozen times. This is not a round trip. This is not a diplomatic mission. This is, at best, a one-way archaeological expedition to a civilization that no longer exists in any form the traveler was briefed about. Fifth problem, and this is the one that I think about most, the one that I find genuinely philosophically disturbing, the return trip. If you want the alien arrival scenario to make any sense, the aliens have to come from somewhere and presumably want to go back. The round trip doubles every number I've already given you. The energy, the time, the radiation exposure, the institutional and civilizational continuity required to sustain a mission over timescales that dwarf most human civilizations. Every number doubled. Every obstacle doubled. Now, some of you are sitting there thinking about wormholes. I know because I've given versions of this argument before, and at this point, someone always leans forward with a particular expression, a hopeful, slightly embarrassed expression, like a child about to ask if Santa Claus is real and they bring up wormholes. Wormholes are real. I want to be clear about that. They are a legitimate solution to Einstein's field equations. General relativity, which is the most successful theory of gravity we have, permits wormholes in principle. A wormhole is a tunnel through space-time connecting two distant regions, 2 points that might be millions of light years apart in normal space, could be connected by a wormhole that is traversable in a short time. This is real physics, not science fiction. But here is what happens when you actually do the physics of traversable wormholes. To keep a wormhole open, to prevent it from collapsing, the instant it forms, you need what physicists call exotic matter, matter with negative energy density. Not matter that has some unusual property, matter that has a negative energy density, which means its energy is less than nothing, which means it is a form of matter that has never been observed, that may not exist, that violates energy conditions, that general relativity itself tends to prefer, and that almost certainly cannot be manufactured in quantities sufficient to hold open a wormhole large enough for a spacecraft. The Casimir effect gives you tiny quantum scale regions of negative energy density between conducting plates. This is real. This has been measured. The negative energy densities involved are real but vanishingly small. We are talking about energies so tiny that scaling them up to stabilize a traversable wormhole would require a machine that, by the best estimates, would have to be larger than the observable universe. There is also the question of stability. Juan Malvicena and others, and this connects to some of my own work, on the ER equals EPR correspondence, which I'll come back to, have shown that the quantum mechanics of wormholes is deeply entangled with the quantum mechanics of black holes, and information in ways that suggest traversable wormholes are extraordinarily difficult to create without first creating conditions that are, to put it gently, inhospitable. The universe protects its causal structure. It does not casually allow you to punch shortcuts through space-time. The mathematics resists consistently, stubbornly. Now here is where it gets strange, in a direction that I think most people don't expect. The Fermi paradox, Enrico Fermi's lunch table question, "Where is everybody?" is usually framed as a problem about communication and civilization. Why haven't we heard from anybody? Why hasn't anybody visited? And the usual responses fall into two camps. Either life is incredibly rare, the universe is mostly empty, and we got lucky, or life is common, but civilizations destroy themselves before they can make contact through war or environmental collapse or some other catastrophe. These are called the great filter hypotheses. Either the filter is behind us, meaning we already survived the hard part, or it is ahead of us, meaning we are probably going to hit it. Both of these framings share an assumption that I want to challenge. Both assume that the silence is biological or sociological in origin. Either life doesn't arise, or it arises and then kills itself. But there is a third option, and it is the option that the physics forces you to consider once you take the distance problem seriously. The silence is geometric. The observable universe is about 93 billion light years in diameter. The Milky Way galaxy, our galaxy, is about 100,000 light years across. Andromeda, our nearest large galactic neighbor, is 2.5 million light years away. The distances between galaxies are so large that even at the speed of light, they represent travel times that exceed the current age of the universe for most journeys we might care about. But even within the Milky Way, the distances between stars are so vast, and the speeds achievable by any massive object are so limited, that the effective communication and travel time between any two random points in the galaxy is measured in tens of thousands to millions of years. What this means is that the galaxy is not one connected space. It is, for any civilization operating below the speed of light, a collection of essentially isolated pockets. A civilization could be extraordinarily advanced, extraordinarily expansive, and still be separated from us by distances that make meaningful contact, two-way communication, let alone physical visitation, effectively impossible on any time scale that means anything to a civilization. Here is the thought experiment I want you to hold in your mind. Imagine a species that evolved on a planet orbiting a star 50,000 light years from Earth. They are intelligent, they have technology, they have been broadcasting radio signals, the alien equivalent of our own leakage radiation, for 10,000 years. Those signals are currently traveling outward from their planet at the speed of light. They have traveled 10,000 light years. They have 40,000 light years still to go before they reach us. By the time those signals arrive, 40,000 years will have passed on Earth. What will Earth look like in 40,000 years? Homo sapiens have existed for roughly 300,000 years, so 40,000 years is not nothing. It is more than 10% of our entire species history. The civilization that might eventually receive that signal is not us. It is whatever we become, or whatever replaces us, or whatever grows from the wreckage if we fail. And that alien civilization, 50,000 light years away, if they sent a spacecraft at the fastest speed any physically plausible drive could achieve, that spacecraft would take a minimum of hundreds of thousands of years to arrive. The civilization that launched it would be unrecognizable, extinct, or transformed beyond all recognition by the time the spacecraft arrived. The mission makes no institutional sense. It makes no biological sense. It makes no civilizational sense. It makes only the sense that a beautiful dream makes, which is a different kind of sense entirely, and one that the universe has never been particularly interested in accommodating. I want to tell you about a conversation I had with Carl Sagan. This was in the early 90s when I was deep in what would become the black hole war, arguing with Hawking about whether information could be destroyed in a black hole. Carl and I had dinner, and Carl was one of the most genuinely optimistic people I ever knew. Not naive. He understood the physics, but he had this deep, almost spiritual conviction that intelligence was not a freak accident, that the universe was in some sense friendly to complexity and mind. He believed, and I respected this, even when I disagreed, that the silence of the cosmos was not emptiness but distance, and that given enough time, minds would reach across that distance. And I said, Carl, The time is the problem. You keep treating time as something you can add more of. The universe has a finite age. Stars have finite lifetimes. Galaxies drift apart at accelerating rates because of dark energy. The window for contact, the actual window, the physical window, is not infinite. It is closing. He didn't have a good answer. Not because he was unintelligent. Carl Sagan was one of the most intellectually formidable people I ever encountered, but because the physics is what it is, and optimism, no matter how well reasoned, doesn't change the equations. Dark energy. Let me talk about dark energy for a moment, because this is the part of the alien problem that most people have not thought through, and it is the part that I find most genuinely unsettling. The universe is expanding. We have known this since Hubble, but in 1998, and this won Nobel Prizes, so I want to be clear, this is not fringe, we discovered that the expansion is accelerating. The galaxies are not just moving apart. They are moving apart faster and faster, driven by something we call dark energy, which pervades empty space and acts as a kind of anti-gravity on cosmological scales. The implications of this are staggering. Galaxies that are currently just barely reachable in principle, galaxies so distant that a signal traveling at the speed of light would take billions of years to reach them, are moving away from us faster than the speed of light due to the expansion of space itself. Not because anything is moving through space faster than light that would violate relativity, but space itself is expanding, and the expansion rate for distant enough regions exceeds the speed of light, which means light can never cross that gap no matter how long you wait. This is not a theoretical curiosity. There is a cosmological event horizon, a surface, like the event horizon of a black hole, but for the entire observable universe beyond which nothing can ever reach us. No signal, no ship, nothing. And that horizon is not enormously far away. It is at a distance of roughly 16 billion light years, and it is shrinking very slowly, but it is shrinking because the acceleration of expansion means that more and more of the universe is crossing over that horizon and becoming permanently unreachable. Any civilization beyond our local group of galaxies is already beyond any practical possibility of contact, not because of our technological limitations, but because space-time itself is pulling us apart faster than light can cross the gap. They might as well be in a different universe, and in the sense that is more than metaphorical, they are. They are in a causally disconnected region of space-time. The laws of physics that govern our relationship to them are the same laws that govern our relationship to the interior of a black hole. The information cannot get out. The visitors cannot arrive. The physics does not permit it. Now, here is where I have to be honest about something. Here is my moment of genuine, productive intellectual discomfort. Everything I have told you tonight about why aliens cannot arrive is grounded in our current best understanding of physics. General relativity, special relativity, thermodynamics, quantum mechanics, cosmology. This is not a weak foundation. These are the most tested, most precisely confirmed theories in the history of science. I trust them more than I trust almost anything else I know. But I have spent my career finding places where our best theories break down. Black holes, the early universe, quantum gravity. The boundary between quantum mechanics and general relativity is a place where the foundations crack, where the most successful theories in physics give you contradictory answers, where the mathematics fails to converge. And I helped find some of those cracks. The black hole information paradox, the problem that Hawking and I fought about for decades, is fundamentally a crack in the foundation, a place where we know our theories are incomplete. I cannot, in good conscience, tell you that a theory of quantum gravity, a theory we do not yet have, that nobody has yet written down in a complete and consistent form, might not reveal some structure of space-time that changes the picture. I don't know what that structure would be, The ER equals EPR correspondence that Juan Malvicena and I developed suggests that quantum entanglement and space-time geometry are related in deep ways that nobody fully understands yet. Whether those connections ever resolve into something that changes the physics of interstellar travel, I genuinely do not know. What I know is this. Every time a physicist has looked at faster-than-light travel or wormhole traversal or any of the mechanisms that the science fiction scenario requires, the mathematics has said no, consistently, across multiple frameworks, across multiple approaches, across multiple generations of physicists trying very hard to find a yes. The universe keeps saying no. And in my experience, when the universe says no that many times in that many different ways, you should probably start believing it. But I want to be clear, and this is the honest part, the part that distinguishes doing physics from doing ideology, that I am not saying the question is settled forever. Physics does not work that way. What I am saying is that the burden of proof lies with the yes, not the no, and the yes is not carrying that burden. Let me come at this from a completely different direction, because I think the best arguments hit the target from multiple angles. Consider the Drake equation. Frank Drake, in 1961, wrote down a famous equation estimating the number of communicating civilizations in our galaxy. It has terms for the rate of star formation, the fraction of stars with planets, the fraction of those planets with life, the fraction of life that develops intelligence, the fraction of intelligent life that develops technology, and the lifetime of such civilizations. Various people have plugged in various numbers, and you get estimates ranging from one just us to millions. The Drake equation is a useful way of organizing ignorance. I say that not dismissively. Organizing ignorance is genuinely valuable in science. But I want to point out what the Drake equation does not contain. It does not contain a term for the probability that a civilization, once it exists and has developed technology, can actually cross the distances involved in interstellar travel. It contains a term for the lifetime of the civilization. But it doesn't ask, during that lifetime, what fraction of space can that civilization actually physically reach? If you add that term, and it is not a term the original equation included, because in 1961, the cosmological constraints I've described were not all fully worked out, the number collapses. Not because civilizations are rare, not because they destroy themselves, but because the fraction of the galaxy that any given civilization can reach in any realistic lifetime is extraordinarily small. The galaxy is not a connected space for sublight travelers. It is a collection of bubbles, each civilization isolated in its own bubble by the sheer scale of the distances involved. Two civilizations could both exist in the Milky Way, both be technological, both be curious, both be sending signals and never know about each other, simply because the signals take longer to arrive than either civilization lasts. Or they both last, but the signals arrive, and by the time a response can be sent, the originating civilization has changed so fundamentally that the conversation is with a ghost. This is the Fermi paradox solved, not by a filter, not by rare life, not by self-destruction, by geometry, by the brutal, indifferent, beautiful geometry of a universe that is simply too large, expanding too fast for the civilizations within it to find each other in any meaningful way. I want to address one more thing before I close, because I know what a certain fraction of this audience is thinking. Some of you are thinking, what about sufficiently advanced civilizations? What about a civilization 1,000,000 years more advanced than us? Surely the physics I have described applies to us, to our level of technology, but 1,000,000 years is a long time. Couldn't they find ways around these constraints that we simply can't imagine? This is the argument from our own ignorance, and I have some sympathy for it, because I've spent my career being surprised by physics. But there is a difference between being surprised within a framework and having the framework dissolved entirely. General relativity has been tested to extraordinary precision. Special relativity has been tested to extraordinary precision. Thermodynamics, the law that you cannot get energy for free, that every process has a cost, that entropy increases, is about as secure as any physical law gets. A sufficiently advanced civilization does not get to opt out of thermodynamics. It does not get to opt out of the speed of light. It does not get to opt out of the cosmological expansion of space-time. These are not technological barriers. They are the rules of the game. The game does not have an opt-out for sufficiently motivated players. When Hawking told people not to attract the attention of aliens, he was doing something that I think was actually harmful, not in its intent. Stephen's intent was always serious and engaged, but in its effect, he was lending his enormous credibility to a scenario that the physics does not support. He was making people take seriously a threat that is not a threat, not because alien civilizations couldn't theoretically exist, but because the physics of getting from there to here is prohibitive in ways that no level of advancement changes. The real question, and this is the question I think we should be spending our intellectual energy on, is not whether they're coming. They're not coming. The real question is what the silence tells us about the structure of the universe, about the nature of life and intelligence, about whether we are a typical or an atypical outcome of the laws of physics. That question is hard and alive and genuinely unsolved and genuinely important. It connects to some of the deepest questions in physics, questions about fine-tuning, about the anthropic principle, about whether the laws of physics are selected in some landscape of possible laws or whether they are unique and necessary and we just don't understand why yet. These are the questions that actually keep me up at night, not will the aliens come? The answer to that is no. The question that keeps me up is why are we here at all? Why does the universe have the laws it has? Why does it permit complexity and life and minds that can ask these questions? Those are real questions. Those are the questions worth losing sleep over. The alien arrival fantasy is, at its core, a human story about loneliness and scale. We look out at the vastness of the universe and we feel small, and our instinct is to populate that vastness with minds like ours, to imagine that intelligence is not a fluke but a feature, that the universe is in the business of producing beings who look up and wonder. I understand that instinct. I share it to some extent. But the job of physics is not to comfort that instinct. The job of physics is to find out what is actually true and to follow the truth wherever it goes, even when it goes somewhere cold and quiet and immense. The universe is cold and quiet and immense. It is also, by the way, extraordinarily beautiful, more beautiful than any of us had any right to expect. The laws of physics are more elegant, more intricate, more surprising than anything a civilization of aliens could have told us. The fact that space-time curves, that information is conserved, that quantum mechanics and gravity are connected through the geometry of entanglement in ways we are only beginning to understand. These are not consolation prizes for the absence of alien visitors. These are the real thing. These are what the universe actually contains, waiting to be understood by minds that are willing to do the work. So here is what I want to leave you with. Not comfort, not despair, a question. If the physics says the universe is structured in a way that prevents minds from finding each other, if geometry and thermodynamics and cosmology conspire to keep every intelligence isolated in its own small bubble of reachable space-time, then what does that tell us about why any of this exists at all? What is a universe for if the minds it produces can never compare notes? What is the point of consciousness arising in a cosmos that is built, apparently deliberately built, to keep consciousness alone? I don't have an answer. I've been thinking about it for 40 years and I don't have an answer. And I will tell you, that's the most interesting place physics can put you. Not with an answer, with a question so good, so sharp, so resistant to easy resolution that you know you're touching something real. That's where we are, right at the edge of something enormous, and we're going to have to figure it out without any help.